Hello, and welcome to this introductory video on the idea of a magnetic field. In this video, we're going to introduce the magnetic field and how to determine its direction, and then in subsequent videos, we'll look at how particles actually interact with the magnetic field. In previous videos, we've seen that a stationary charge gives rise to an electric field. We've learned how to describe it, etc. In this video, we're focusing on the magnetic field. And the magnetic field is closely related. It is actually created by a moving charge. So whenever you've got some charge which is moving around, of course it's creating an electric field, but it is also creating a magnetic field now that it's moving. Okay. In terms of how we describe this thing, we used E for an electric field. We're going to use the letter B to represent our magnetic field. And B officially is actually a vector. So keep that in mind as well. It's got some direction. So let's think about how we're going to determine that direction. It's going to be given by a right-hand rule, but we have a couple of choices for how our charge is moving. Let's take a look at two specific cases. In one case, we'll just have a wire, and we'll have some current flowing through there. So let's go ahead and do that sort of thing. So there's some current flowing through that wire. The other common case that we might want to consider is if we've got a coil going around like that and going back to being a wire. Okay, and let's just say that the current I in this case will be going that way. So I will replace this diagram with a better one. There you go. In this diagram now it's clear which side is to the front and which side is to the back. Okay, it's going to be important in a second. So we have a right-hand rule, actually we have two, to describe what's going on with these cases, which direction is the magnetic field. Now, when you have a moving charge, the interesting thing about the magnetic field is it's going to loop around that moving charge, and now we just need to specify which direction are we looping. So the right-hand rule for the first case, if you've got some nice linear motion, then you go ahead and let your thumb be the direction of that current. And as you're doing that, your fingers naturally curl around that wire in the direction that the B field is going. So in this case, it is going into the board on that side. Sorry, into the board on that side, and out of the board on this side. It's coming towards me here, in there, towards here. So you just draw some dots and some X's, and that's what it means. And we really mean that it's a nice continuous circle around here, going like that. All right, and then for the coil, the rule is swap things around. Let your fingers curl in the direction of the current, and then your thumb will point the direction. And so now you see why it's important that I specify which side of the coil is to the front, because I could either be going down in front and up in the back, or going up in front of the coil closer to you, and then down in the back. In that case, the B field would be that way, versus if it's going down in the front and going up in the back. All right, so that's how the right-hand rule works. We're going to see lots of important dynamics as we continue on in studying this, but this is how you figure out what the magnetic field due to some moving charges is going to look like. The units for the magnetic field are, again, really compound units, but we introduce, as we sort of have been doing for every single thing in electromagnetism, its own special unit. We call the units of magnetic field a Tesla. And this Tesla is equal to a Newton per Coulomb per meter squared, which is also equal to a Newton per amp meter. Okay. So those are the units, and that is how you describe the magnetic field.